Imagine a planet where it rains glass sideways, or a world so hot that its surface is a sea of molten lava. These aren't scenes from a science fiction movie, they're real places, out there in the vast expanse of space, defying everything we thought we knew about planetary systems. What if I told you that the universe is far stranger, more mysterious, and more unpredictable than we ever imagined? Today, we're diving into 25 of the most bizarre and mind-bending discoveries about planetary systems, discoveries that challenge our understanding of how planets form, behave, and even survive. From diamond worlds to planets with triple sunsets, these findings will leave you questioning everything you thought you knew about the cosmos. So, buckle up and get ready to explore the weird, the wild, and the utterly unexpected. By the end of this journey, you'll see the universe in a whole new light. Let's begin. Now, let's turn our attention to a discovery that sounds like it belongs in a treasure chest rather than in space. Meet 55 Cancri E, a planet so extraordinary that it's often referred to as the Diamond Planet. Located about 40 light-years away from Earth, this world is believed to be composed largely of carbon, with a significant portion of it crystallized into diamond. Yes, you heard that right, diamond. Scientists estimate that this planet could contain up to 3 times the mass of Earth in diamond alone. But how does such a glittering world come to exist? The story of 55 Cancri E begins with its star, which is rich in carbon. As the planet formed, the intense pressure and heat caused the carbon within it to crystallize, creating vast quantities of diamond. This process is similar to how diamonds form deep within Earth's mantle, but on a planetary scale. What makes 55 Cancri E even more fascinating is its extreme environment. It orbits its star so closely that a single year lasts just 18 hours, and surface temperatures can reach a scorching 2,700 degrees Celsius. These conditions make it one of the most hostile worlds ever discovered, but the implications of this discovery go far beyond its dazzling composition. 55 Cancri E challenges our understanding of planetary formation and diversity. It shows us that planets can form in ways we never imagined, with materials and conditions that seem almost otherworldly. This discovery also raises intriguing questions about the potential for carbon-rich planets elsewhere in the universe. Could there be other diamond worlds out there waiting to be found? As we marvel at the brilliance of 55 Cancri E, it's clear that this planet is more than just a cosmic gem. It's a window into the incredible variety and complexity of planetary systems. And as we move forward, we'll uncover even more wonders that push the boundaries of what we thought was possible. Next up, we'll explore a planet that doesn't just have one sun, but 3. Stay tuned. Now, let's journey to a world that defies the very idea of a single sun in the sky. Imagine a planet where not 1, not 2, but 3 suns rise and set in a cosmic dance that lasts for centuries. This is HD 131,399 AB, a planet located about 340 light-years from Earth, nestled in a triple star system. Unlike anything in our solar system, this planet orbits one star while 2 others twirl around it in a complex gravitational ballet. The most striking feature of HD 131,399 AB is its unique orbit. It circles its primary star at a distance roughly twice that of Pluto's orbit around our Sun, taking about 550 Earth years to complete a single trip. Meanwhile, the other 2 stars orbit each other at a much closer distance, creating a dynamic and ever-changing sky for the planet. For part of its year, HD 131,399 AB experiences constant daylight as all 3 stars are visible in the sky. At other times, it enjoys triple sunrises and sunsets, a spectacle that would make even the most imaginative science fiction writers envious. But this planetary system isn't just a marvel to behold, it's a puzzle for scientists. The existence of HD 131399 AB challenges our understanding of how planets form and survive in such chaotic environments. Typically, the gravitational forces in a multi-star system would disrupt the formation of planets, making it nearly impossible for them to maintain stable orbits. Yet, HD 131399 AB not only exists but thrives, raising questions about the resilience and adaptability of planetary systems. How did this planet form in such a turbulent environment? And what does its survival tell us about the potential for other planets in similar systems? This discovery also opens up new possibilities for the diversity of planetary systems in the universe. If a planet can exist in a triple star system, what other strange and unexpected configurations might be out there? HD 131399 AB reminds us that the universe is far more inventive than we often give it credit for, constantly challenging our assumptions and expanding our horizons. As we leave this three-sunned wonder behind, we'll turn our attention to a planet that doesn't even have a star to call home. Stay with us as we explore the mysterious world of rogue planets, drifting alone through the vastness of space. Now, let's venture into the lonely expanse of space where planets drift without the warmth or light of a star to guide them. These are rogue planets, celestial wanderers untethered from any solar system. Among them is CFBD SIR 21490403, a mysterious world floating freely through the galaxy about 100 light-years from Earth. Unlike the planets we're familiar with, this rogue planet doesn't orbit a star. It's completely independent, moving through the darkness of interstellar space. Rogue planets like CFBD SIR 21490403 challenge our traditional understanding of what a planet is. Typically, planets are defined as objects that orbit a star, but these free-floating worlds defy that definition. Scientists believe they may have formed in one of two ways. Either they were ejected from their original star systems due to gravitational interactions, or they formed on their own, much like stars, but without enough mass to ignite nuclear fusion. CFBD SIR 21490403, for instance, is thought to be a young planet, still glowing faintly from the heat of its formation, making it easier to detect despite its lack of a star. What makes rogue planets so fascinating is their ability to survive in the harsh conditions of interstellar space. Without a star to provide warmth, these planets are incredibly cold, with surface temperatures plunging to hundreds of degrees below zero. Yet they persist, drifting through the galaxy for billions of years. Some scientists even speculate that rogue planets could host life, hidden beneath icy surfaces or within subsurface oceans kept warm by internal heat. While this remains speculative, it opens up intriguing possibilities for the potential habitability of these isolated worlds. The discovery of CFBD SIR 21490403 and other rogue planets forces us to rethink the boundaries of planetary science. If planets can exist without stars, what does that mean for our understanding of how planetary systems form and evolve? These free-floating worlds remind us that the universe is full of surprises, constantly challenging our assumptions and expanding the possibilities of what we might find. As we leave the lonely journey of rogue planets behind, we'll turn our attention to a world that's anything but cold and dark. Next, we'll explore Kepler 10b, a scorching lava world where the surface is so hot it's literally melting. Stay with us as we uncover the fiery secrets of this extreme planet. Now, let's shift our gaze from the icy solitude of rogue planets to a world that burns with an intensity unlike anything we've seen before. Welcome to Kepler 10b, a planet so scorching that its surface is a sea of molten lava. Located about 560 light-years from Earth, this fiery world orbits its star so closely that a single year lasts less than one Earth day. The proximity to its star means Kepler 10b is constantly bombarded with heat, raising its surface temperatures to a staggering 1,700 degrees Celsius, hot enough to melt rock into rivers of lava. Kepler-10b is a prime example of what scientists call a lava world, a type of exoplanet where extreme heat transforms the surface into a molten landscape. Unlike Earth, which has a solid crust and a dynamic mantle beneath, Kepler-10b's entire surface is likely in a perpetual state of melting and solidifying. This creates a chaotic environment where lava flows and volcanic activity dominate, offering a glimpse into the violent processes that shape planets in their early stages of formation. What makes Kepler-10b particularly fascinating is how it challenges our understanding of planetary evolution. Planets like this are thought to form close to their stars, where temperatures are high enough to vaporize lighter materials, leaving behind dense, rocky cores. Over time, these planets may migrate inward, drawn by the gravitational pull of their stars, until they settle into ultra-close orbits. Kepler-10b's extreme conditions provide a window into this process, showing us how planets can evolve under intense heat and pressure. But the story of Kepler-10b doesn't end with its molten surface. Scientists believe that the planet's high density suggests it has a massive iron core, possibly making up a significant portion of its mass. This raises questions about how such a dense planet could form so close to its star. Some theories suggest that Kepler-10b may have lost much of its outer layers due to the intense heat, leaving behind a dense metallic core. Others propose that it could have formed farther out in its system and migrated inward, shedding its lighter materials along the way. Kepler-10b's extreme environment also offers clues about the diversity of planetary systems. While Earth-like planets with temperate climates are often the focus of the search for life, worlds like Kepler-10b remind us that the universe is full of extremes. These lava worlds, though inhospitable to life as we know it, play a crucial role in helping us understand the range of conditions under which planets can form and evolve. As we leave the molten chaos of Kepler-10b behind, we'll turn our attention to a planet where the weather is just as bizarre, but in a completely different way. Next, we'll explore HD 189733b, a world where it rains glass sideways. Stay with us as we uncover the strange and fascinating weather patterns of this distant planet. Now, let's journey from the molten inferno of Kepler-10b to a world where the weather is as strange as it is deadly. Meet HD 189733b, a planet where the skies rain glass sideways. Located about 63 light-years from Earth, this cobalt-blue exoplanet is a gas giant, similar in size to Jupiter, but its atmosphere is anything but ordinary. The planet's vivid blue hue might make it look serene from a distance, but up close, it's a place of unimaginable chaos. HD 189733b's atmosphere is filled with silicate particles, tiny grains of sand-like material that, under the planet's extreme conditions, form into glass. These particles are whipped around by winds that reach speeds of up to 5,400 miles per hour, 7 times the speed of sound. Imagine standing on this planet, if you could, and being pelted by shards of glass hurtling through the air at unimaginable speeds. It's a weather system that defies everything we know about atmospheric conditions. What makes this glass rain even more bizarre is the planet's proximity to its star. HD 189733b orbits so close that its year lasts just 2.2 Earth days, and its surface temperature soars to around 900 degrees Celsius. The intense heat vaporizes the silicate particles, which then condense into tiny glass droplets as they cool in the upper atmosphere. These droplets are swept up by the planet's supersonic winds, creating a relentless, sideways rain of molten glass. But the strangeness doesn't stop there. HD 189733b is tidally locked, meaning one side always faces its star while the other remains in perpetual darkness. This creates a stark temperature contrast between the day and night sides, driving the planet's extreme weather patterns. The constant bombardment of stellar radiation also strips away the planet's atmosphere over time, creating a comet-like tail of escaping gases. It's a world where the very air is being torn away, leaving behind a trail of destruction. Scientists study planets like HD 189733b, not just for their bizarre weather, but for what they can teach us about the diversity of planetary atmospheres. While Earth's weather is driven by water vapor and air currents, HD 189733b shows us how different materials and conditions can create entirely new kinds of atmospheric phenomena. It's a reminder that the universe is full of surprises, and even the most extreme environments can offer valuable insights into the processes that shape planets. As we leave the glass-strewn skies of HD 189733b behind, we'll turn our attention to a planet that's as light as a feather yet defies our understanding of planetary formation. Next, we'll explore Kepler 51b, a super-puff planet with a density so low it's often compared to cotton candy. Stay with us as we unravel the mysteries of this fluffy giant. Now, let's shift our gaze from the glass-strewn chaos of HD 189733b to a planet that seems to defy the very laws of physics. Meet Kepler 51b, a world so light and fluffy that scientists have nicknamed it the cotton candy planet. Located approximately 2,400 light-years from Earth, this gas giant is unlike anything we've encountered in our own solar system. Its density is so low that if you could place it in a cosmic bathtub, it would float like a balloon. But how does such a planet even exist, and what keeps it from collapsing under its own weight? Kepler 51b is part of a rare class of exoplanets known as super-puffs, characterized by their incredibly low densities. Despite being roughly the size of Jupiter, this planet has a mass only a fraction of Earth's. To put it into perspective, if Jupiter were a bowling ball, Kepler 51b would be a wispy cloud of cotton candy. This extreme lightness is due to its atmosphere, which is composed mostly of hydrogen and helium, but is so puffed up that it extends far beyond what we'd expect for a planet of its size. Scientists believe that the planet's atmosphere is bloated, possibly due to intense heat from its star or internal processes that cause it to expand. But the mystery doesn't end there. Kepler 51b orbits its star at a distance closer than Mercury does to our Sun, completing a full orbit in just 45 Earth days. This proximity means the planet is constantly bombarded by stellar radiation, which could be contributing to its inflated state. However, the exact mechanisms behind its formation and maintenance remain a puzzle. Some theories suggest that Kepler 51b might have formed farther out in its system and migrated inward, while others propose that it could be losing its atmosphere over time, slowly shrinking as it ages. What makes Kepler 51b particularly fascinating is what it reveals about the diversity of planetary systems. While most gas giants we've discovered are dense and compact, super-puff planets like Kepler 51b challenge our understanding of how planets form and evolve. They remind us that the universe is full of surprises, and even the most seemingly impossible worlds can exist under the right conditions. Studying these planets helps scientists refine their models of planetary formation, offering clues about the processes that shape the cosmos. As we leave the ethereal world of Kepler 51b behind, we'll turn our attention to a planet that's not just strange but also tragic. Next, we'll explore WASP-12b, a planet that's being slowly devoured by its own star, leaving behind a comet-like tail. Stay with us as we uncover the fate of this doomed world. Now, let's journey from the fluffy, ethereal world of Kepler 51b to a planet that's facing a far more dramatic fate. Meet WASP-12b, a gas giant that's not just orbiting its star but is being consumed by it. This doomed planet, located around 870 light-years from Earth, is locked in a cosmic dance of destruction, leaving behind a spectacular comet-like tail as it slowly evaporates into space. WASP-12b is what scientists call a hot Jupiter, a type of exoplanet that orbits incredibly close to its star. In fact, it's so close that it completes an orbit in just over one Earth day. This proximity subjects the planet to extreme temperatures, with its day side reaching a scorching 2,200 degrees Celsius hotter than some stars. But what makes WASP-12b truly unique is the way its star is tearing it apart. The intense gravitational forces from the star are pulling material off the planet's atmosphere, creating a vast, glowing tail that stretches millions of kilometers into space. This process, known as planetary evaporation, is transforming WASP-12b into a cosmic spectacle. The evaporation of WASP-12b is driven by the star's immense heat and gravitational pull. As the planet's atmosphere heats up, it expands and escapes into space, forming a tail of gas and dust. This tail is composed mostly of hydrogen and helium, the same elements that make up the planet's atmosphere. Over time, this process will strip WASP-12b of its outer layers, leaving behind a dense, rocky core. Scientists estimate that the planet could lose as much as one Earth mass every billion years, a rate that suggests it may not survive for much longer in cosmic terms. What's particularly fascinating about WASP-12b is how it challenges our understanding of planetary survival. Most planets we've discovered are stable, enduring objects, but WASP-12b is a reminder that not all worlds are so fortunate. Its evaporation provides a rare opportunity to study the end stages of a planet's life, offering insights into the forces that shape planetary systems. By observing WASP-12b, scientists can learn more about how stars interact with their planets and how these interactions can lead to dramatic transformations. As we leave the tragic tale of WASP-12b behind, we'll turn our attention to a planet that feels like it's straight out of a science fiction movie. Next, we'll explore Kepler-16b, a world that orbits two stars, creating a double sunset that's as mesmerizing as it is scientifically significant. Stay tuned as we uncover the secrets of this binary star system and the planet that calls it home. Now, let's step into a scene that feels like it's been plucked straight from a science fiction epic. Imagine standing on a distant world, gazing up at not one but two suns setting on the horizon. This isn't a scene from Star Wars, it's the reality of Kepler-16b, a planet that orbits two stars, creating a breathtaking double sunset. Located approximately 245 light-years from Earth, Kepler-16b is one of the first confirmed circumbinary planets, meaning it orbits both stars in a binary system. Kepler-16b's two stars are a pair of smaller, cooler stars compared to our Sun. The primary star is about 69% the mass of the Sun, while its companion is much smaller, at just 20% of the Sun's mass. These two stars orbit each other every 41 days, and Kepler-16b circles them both in a wide, stable orbit that takes about 229 Earth days to complete. This unique arrangement creates a dynamic and ever-changing sky for any hypothetical observer on the planet's surface. The discovery of Kepler-16b was groundbreaking because it proved that planets could form and survive in binary star systems, a scenario once thought to be too chaotic for stable planetary orbits. The gravitational dance between the two stars and the planet is a delicate balance, but Kepler-16b manages to maintain its orbit without being flung into space or pulled into one of the stars. This discovery opened up new possibilities for finding planets in systems with multiple stars, which are surprisingly common in our galaxy. What makes Kepler-16b even more fascinating is how it challenges our understanding of planetary formation. In a binary system, the gravitational forces from two stars can disrupt the protoplanetary disk of dust and gas from which planets form. Yet, Kepler-16b not only exists but also provides a glimpse into how planets can adapt to such complex environments. Its discovery has led scientists to rethink the conditions necessary for planet formation, suggesting that even in seemingly hostile systems, worlds can thrive. As we marvel at the beauty and complexity of Kepler-16b, we're reminded of the incredible diversity of planetary systems in the universe, but our journey doesn't end here. Next, we'll venture to a planet so hot that its atmosphere is filled with metals, a world where the very air you breathe would be unlike anything found on Earth. Stay with us as we uncover the mysteries of Kelt 9b, the hottest known exoplanet. Now, let's turn our attention to a world that defies imagination with its scorching temperatures and bizarre atmosphere. Meet Kelt 9b, a planet so hot that it makes even the most extreme environments on Earth seem mild in comparison. Located roughly 670 light-years away, Kelt 9b holds the title of the hottest known exoplanet, with surface temperatures soaring to an astonishing 4,000 degrees Celsius hotter than some stars. What makes Kelt 9b truly extraordinary is its atmosphere, which is rich in metals. Under such extreme heat, elements like iron and titanium, which would typically remain solid on cooler planets, are vaporized into gases. This creates a surreal environment where the very air is filled with metallic vapors, a phenomenon unlike anything we've encountered in our own solar system. The planet's host star, Kelt 9, plays a significant role in shaping this fiery world. It's a blue giant nearly twice as hot as our Sun, and bombards Kelt 9b with intense ultraviolet radiation. This relentless heat not only vaporizes metals but also strips away the planet's atmosphere at an alarming rate, creating a comet-like tail of escaping gases. Scientists estimate that Kelt 9b is losing millions of tons of its atmosphere every second, a process that could eventually leave it as little more than a barren core. Kelt 9b's extreme conditions challenge our understanding of planetary atmospheres and their resilience. While most planets we study have atmospheres dominated by gases like hydrogen, helium, or carbon dioxide, Kelt 9b's metal-rich air opens up new questions about the diversity of atmospheric compositions in the universe. It also raises intriguing possibilities about how planets form and evolve under such intense stellar radiation. As we ponder the mysteries of Kelt 9b, we're reminded once again of the incredible variety of worlds that exist beyond our solar system. But the surprises don't end here. Next, we'll explore a planet that defies all expectations by existing in a place where it shouldn't, a world that challenges our very understanding of planetary survival. Stay with us as we uncover the enigma of LTT 9779b, a planet in the so-called Neptune Desert. Now, let's journey to a planet that seems to break all the rules, a world that shouldn't exist yet somehow does. Meet LTT 9779b, a planet that has left scientists scratching their heads due to its unlikely location in what astronomers call the Neptune Desert. This mysterious region of space is known for its scarcity of Neptune-sized planets orbiting close to their stars, making LTT 9779b a true cosmic anomaly. LTT 9779b is roughly the size of Neptune, but it orbits its star at an incredibly close distance, completing a full orbit in just 19 hours. This proximity means the planet is subjected to extreme heat and radiation, conditions that typically strip away the atmospheres of similar-sized planets, leaving behind only rocky cores. Yet, against all odds, LTT 9779b has managed to retain a thick, puffy atmosphere, defying the expectations of planetary survival. What makes this planet even more puzzling is its density. Unlike most Neptune-sized planets, which are either gas giants or rocky worlds, LTT 9779b appears to have a unique composition. Its atmosphere is rich in heavy metals, and its core is unusually dense, suggesting a complex and unexpected formation process. Scientists speculate that it may have migrated inward from a cooler, more distant orbit. but how it managed to survive this journey without losing its atmosphere remains a mystery. The existence of LTT 9779b challenges our understanding of planetary formation and evolution. It raises questions about how planets can endure in such hostile environments and what mechanisms might allow them to retain their atmospheres under extreme conditions. This discovery also highlights the diversity of planetary systems, reminding us that the universe is full of surprises that defy our current models. As we marvel at the resilience of LTT 9779b, we're reminded that the cosmos is far more complex and unpredictable than we often assume. But the wonders of space don't stop here. Next, we'll explore a planet where time moves at an astonishing pace, a world where a single year lasts just 18 hours. Stay with us as we uncover the secrets of TOI 849b, a planet that redefines our understanding of orbital dynamics. Now, let's turn our attention to a planet where time seems to fly by at an almost unimaginable speed. Meet TOI 849b, a world that completes an entire year in just 18 hours. Yes, you heard that right, 18 hours. This incredibly short orbital period makes TOI 849b one of the fastest orbiting planets ever discovered, and it challenges our understanding of how planetary systems can form and evolve. TOI 849b is a rocky planet, roughly 40 times the mass of Earth, but it orbits its star so closely that it's practically skimming the surface. This proximity subjects the planet to extreme temperatures, reaching up to 1,500 degrees Celsius, hot enough to melt most metals. Despite its scorching environment, TOI 849b has managed to hold onto its rocky structure, making it a rare example of a hot super-Earth. What makes this planet particularly fascinating is its unusual history. Scientists believe that TOI 849b might have once been a gas giant, similar to Jupiter or Saturn, but its atmosphere was stripped away over time due to the intense heat and radiation from its star. What remains is a dense, exposed core, a planetary relic that offers a unique glimpse into the inner workings of gas giants. This discovery raises intriguing questions about how planets lose their atmospheres and what happens to their cores when they do. The rapid orbit of TOI 849b also has broader implications for our understanding of planetary systems. It suggests that planets can form much closer to their stars than previously thought, and it challenges the traditional models of planetary migration. How did TOI 849b end up so close to its star? Was it always there, or did it migrate inward over time? These are questions that continue to puzzle astronomers, and studying TOI 849b could provide valuable insights into the dynamics of planetary formation and evolution. As we ponder the mysteries of TOI 849b, we're reminded once again of the incredible diversity of planetary systems in our universe, but the surprises don't end here. Next, we'll venture to a planet with a ring system so massive, it makes Saturn's iconic rings look like a mere accessory. Stay tuned as we explore the astonishing world of J1407b, where the rings stretch farther than the distance between the Earth and the Sun. Now, let's shift our gaze to a planet that takes the concept of planetary rings to an entirely new level. Meet J1407b, a world whose ring system is so colossal, it makes Saturn's iconic rings look like a delicate bracelet in comparison. This extraordinary planet, located over 430 light-years away, boasts a ring system that stretches over 180 million kilometers, more than 200 times wider than Saturn's rings, and even larger than the distance between the Earth and the Sun. J1407b's rings are not just vast, they're also incredibly complex. Unlike Saturn's relatively uniform rings, J1407b's system is divided into dozens of distinct bands, separated by gaps that suggest the presence of moons or other celestial bodies shaping their structure. These gaps, known as shepherd moons, act like cosmic sculptors, carving out paths within the rings and maintaining their intricate patterns. But how did such a massive ring system form in the first place? Scientists believe that J1407b's rings are likely remnants of the planet's formation process. As the planet coalesced from a swirling disk of gas and dust, some of this material remained in orbit, eventually forming the vast rings we see today. Over time, gravitational interactions with moons and other objects may have shaped and refined the rings, creating the stunning complexity we observe. What's even more fascinating is that J1407b's rings are relatively young on a cosmic scale, estimated to be only a few million years old. This suggests that we're witnessing a planetary system in the midst of its evolution, offering a rare opportunity to study how ring systems form and change over time. The discovery of J1407b challenges our understanding of planetary rings and raises intriguing questions about their role in planetary systems. Could such massive rings influence the formation of moons or even planets? How do they interact with their host star and other celestial bodies? These are questions that astronomers are eager to explore as they continue to study this remarkable world. As we marvel at the sheer scale and beauty of J1407b's rings, we're reminded of the endless wonders that await us in the cosmos, but the surprises don't stop here. Next, we'll journey to a planet shrouded in a thick, methane-rich atmosphere, where the skies hold secrets that could reshape our understanding of planetary atmospheres. Stay tuned as we uncover the mysteries of J1414b. Now, let's turn our attention to a world where the skies are anything but ordinary. J1414b, a planet located approximately 40 light-years from Earth, is shrouded in a thick, methane-rich atmosphere that defies our expectations of what planetary skies can look like. This enigmatic world, often referred to as a super-Earth, due to its size larger than Earth but smaller than gas giants like Neptune, offers a glimpse into the diversity of atmospheres that exist beyond our solar system. What makes J1414b so intriguing is its atmosphere, which is dominated by methane, a gas that plays a significant role in shaping the planet's climate and weather patterns. Methane, combined with other gases like water vapor and hydrogen, creates a dense, hazy blanket that obscures the planet's surface from view. This thick atmosphere not only makes J1414b appear as a featureless, cloudy world, but also presents unique challenges for astronomers trying to study it. One of the biggest hurdles in understanding J1414b is the difficulty of peering through its dense atmosphere. Traditional methods of studying exoplanets, such as analyzing the light that passes through their atmospheres, are complicated by the thick haze. This haze scatters and absorbs light, making it hard to determine the planet's composition and surface conditions with precision. Despite these challenges, scientists have managed to gather some clues about J1414b's atmosphere using advanced techniques such as spectroscopy, which analyzes the wavelengths of light to identify chemical signatures. The presence of methane in such abundance raises fascinating questions about the planet's formation and evolution. Methane is typically associated with colder environments, like those found on icy moons or distant planets in our solar system. However, J1414b orbits relatively close to its host star, suggesting that its atmosphere might be shaped by a complex interplay of heat, pressure, and chemical reactions. Could this methane-rich atmosphere be the result of geological activity, or does it hint at a unique history of planetary formation? These are questions that continue to puzzle researchers. Studying J1414b also has broader implications for our understanding of exoplanets. Its thick, methane-dominated atmosphere challenges our assumptions about how planetary atmospheres form and evolve, especially in systems different from our own. By unraveling the mysteries of GJ 1214b, scientists hope to gain insights into the diversity of atmospheres that might exist on other worlds, including those that could potentially support life. As we ponder the secrets hidden within GJ 1214b's hazy skies, we're reminded of the incredible variety of planetary systems that exist in the universe. But our journey doesn't end here. Next, we'll explore a planet that defies the rules of orbital motion, spinning in the opposite direction of its star's rotation. Join us as we uncover the strange story of WASP-17b, a world that orbits backward. Now, let's shift our gaze to a planet that seems to defy the very rules of motion we take for granted. WASP-17b, a gas giant located about 1,000 light-years from Earth, has a peculiar claim to fame. It orbits its star in the opposite direction of the star's rotation. This backward orbit, known as a retrograde orbit, is a rare and puzzling phenomenon that challenges our understanding of how planets form and behave. Most planets in our solar system, and indeed in most known planetary systems, orbit their stars in the same direction as the star's rotation. This alignment is thought to be a natural consequence of the way planets form from a spinning disk of gas and dust. However, WASP-17b bucks this trend, spinning in the opposite direction like a cosmic rebel. So, how does a planet end up with such an unusual orbit? Scientists have proposed several theories to explain this backward motion. One leading idea suggests that gravitational interactions with another massive object, such as a nearby planet or passing star, could have disrupted WASP-17b's original orbit. Over time, these gravitational tugs might have flipped the planet's orbit, sending it spiraling in the opposite direction. Another possibility is that WASP-17b formed in a turbulent environment where the protoplanetary disk itself was misaligned with the star's rotation, setting the stage for its retrograde motion from the very beginning. The discovery of WASP-17b has profound implications for our understanding of planetary systems. It shows that not all planets follow the same orderly patterns we see in our solar system. Instead, some worlds are shaped by chaotic and dynamic processes that can lead to unexpected outcomes. This retrograde orbit also raises questions about the stability and longevity of such systems. Could a backward orbiting planet eventually realign itself, or is it destined to remain a cosmic outlier? Studying WASP-17b and its unusual orbit provides valuable insights into the diversity of planetary systems. It reminds us that the universe is full of surprises, and even the most fundamental rules of motion can be bent or broken under the right conditions. As we continue to explore the cosmos, discoveries like WASP-17b challenge us to rethink our assumptions and expand our understanding of how planets form and evolve. With this backward orbiting world in mind, let's now turn our attention to another extraordinary planet, one that loses its atmosphere in a manner eerily similar to a comet. Join us as we uncover the mysteries of GJ 436b, a planet with a comet-like atmosphere that's slowly evaporating into space. Now, let's journey to a world that's slowly fading away, one particle at a time. GJ 436b, a Neptune-sized exoplanet located about 33 light-years from Earth, is a planet with a comet-like atmosphere that's evaporating into space. This extraordinary phenomenon makes GJ 436b one of the most intriguing and mysterious worlds we've discovered so far. Unlike most planets which hold onto their atmospheres tightly, GJ 436b is shedding its outer layers at an astonishing rate. This process, known as atmospheric escape, creates a long, glowing tail of gas that trails behind the planet, much like the tail of a comet. Scientists believe that the intense radiation from its host star is heating the planet's atmosphere, causing it to expand and eventually escape into space. Over time, this relentless stripping could leave GJ 436b as little more than a barren core. What makes GJ 436b even more fascinating is the composition of its atmosphere. Observations suggest that it's rich in hydrogen, which is being blown away by the star's radiation. This creates a dramatic visual effect with the planet's tail stretching far into space. But this isn't just a cosmic spectacle, it's a window into the complex interactions between stars and their planets. GJ 436b's atmosphere is a living laboratory, offering clues about how planets lose their atmospheres and how these processes shape their evolution. The implications of GJ 436b's comet-like atmosphere are profound. It challenges our understanding of how planets retain or lose their atmospheres over time. For example, could Earth's atmosphere one day face a similar fate? While our planet is much farther from the Sun and has a stronger magnetic field to protect it, GJ 436b reminds us that atmospheric loss is a real and ongoing process in the universe. Studying GJ 436b also provides insights into the diversity of planetary systems. It shows that not all planets are stable, unchanging worlds. Some are dynamic and transient, shaped by the relentless forces of their environments. This discovery raises new questions about the lifespan of planets and the conditions that determine whether they thrive or wither away. As we continue to explore the cosmos, GJ 436b stands as a testament to the incredible variety of planetary systems. It's a world that's both beautiful and fleeting, a reminder that even the most stable-seeming planets can undergo dramatic changes. With this in mind, let's now turn our attention to another extraordinary planet, one where the concept of day and night takes on a whole new meaning. Join us as we explore Kepler-16b, a tidally locked planet with a permanent day side and a permanent night side. Now, let's step into a world where time stands still, or at least where day and night are locked in an eternal embrace. Kepler-16b, a planet orbiting two stars in a system reminiscent of Tatooine from Star Wars, is a tidally locked world. This means one side of the planet perpetually faces its stars, basking in endless daylight, while the other side is shrouded in perpetual darkness. On the day side of Kepler-16b, temperatures soar to unimaginable extremes. The constant bombardment of stellar radiation creates a scorching, inhospitable environment where nothing we know could survive. Imagine a landscape where the ground glows with heat and the atmosphere is a swirling cauldron of superheated gases. It's a place where the concept of a sunset doesn't exist, just an unending, blazing glare. In stark contrast, the night side of Kepler-16b is a frozen wasteland. Shielded from the star's warmth, temperatures plummet to levels that would make even the coldest regions of Earth seem mild. Here, the air is still, and the ground is likely covered in ice or frozen gases. The transition between these two extremes is a narrow band of twilight, where conditions might be just right for some form of exotic weather or even the faint possibility of liquid water. The tidal locking of Kepler-16b is a result of its close orbit around its binary stars. Over time, the gravitational forces from these stars have slowed the planet's rotation until one side always faces inward. This phenomenon isn't unique to Kepler-16b. Our own moon is tidally locked to Earth, but it's rare to see it in a planet orbiting two stars. What makes Kepler-16b particularly fascinating is how it challenges our understanding of habitability. While the day and night sides are extreme, the twilight zone between them could, in theory, offer a narrow strip of stability. Could life exist in such a precarious balance? It's a tantalizing question that pushes the boundaries of what we consider possible in the universe. Kepler-16b also serves as a reminder of the incredible diversity of planetary systems. Not all worlds are like Earth with its predictable cycles of day and night. Some are locked in a cosmic dance where the rules of time and light are rewritten. As we continue to explore the cosmos, discoveries like Kepler-16b remind us that the universe is full of surprises, each one more extraordinary than the last. With this in mind, let's now turn our attention to a planet where storms rage on a scale that defies imagination. Join us as we explore HD 80606b, a world with a storm system so massive it dwarfs anything we've ever seen on Earth. Now let's venture into a world where chaos reigns supreme, a planet where storms rage on a scale so vast they make Earth's hurricanes look like gentle breezes. HD 80606b, a gas giant located about 190 light-years from Earth, is home to one of the most extreme weather systems ever discovered. This planet's storms are not just large, they're colossal, stretching across thousands of miles and unleashing winds that reach speeds of over 5,000 miles per hour. What makes HD 80606b's storms so extraordinary is their sheer intensity and the planet's unique orbit. Unlike Earth, which has a relatively stable climate, HD 80606b follows an elongated, egg-shaped path around its star. This means the planet experiences wild temperature swings as it moves closer to and farther from its star. At its closest approach, the surface heats up to a blistering 2,000 degrees Fahrenheit, while at its farthest point it cools dramatically. These extreme temperature changes fuel the planet's monstrous storms, creating a turbulent atmosphere that never settles. The dynamics of these storms are unlike anything we've seen in our solar system. On Earth, hurricanes form over warm ocean waters and are driven by the planet's rotation. But on HD 80606b, the storms are powered by the planet's rapid heating and cooling combined with its fast rotation. The result is a chaotic, ever-changing atmosphere where storms can grow to cover entire continents, if the planet had any. Instead, these storms swirl endlessly across the planet's gaseous surface, creating a spectacle of nature that's both awe-inspiring and terrifying. Scientists believe that studying HD 80606b could provide valuable insights into the behavior of extreme weather on other planets. By understanding how these storms form and evolve, we can better predict the conditions on distant worlds, especially those with similarly eccentric orbits. It's a reminder that the universe is full of environments far more extreme than anything we've encountered on Earth. As we marvel at the sheer scale of HD 80606b storms, we're reminded of the incredible diversity of planetary systems. From scorching lava worlds to frozen wastelands, and now to a planet where storms dwarf our own, the cosmos continues to challenge our understanding of what's possible. Next, we'll explore a planet with an atmosphere so rich in carbon, it could potentially form diamonds, a world that defies our expectations of planetary chemistry. Now, let's shift our gaze to a planet that seems to defy the very laws of chemistry, a world where the atmosphere is so rich in carbon that it could potentially rain diamonds. Meet WASP-12b, a gas giant located roughly 870 light-years from Earth. This planet is not just another hot Jupiter. It's a cosmic laboratory where extreme conditions create a carbon-dominated environment unlike anything we've ever seen. WASP-12b's atmosphere is packed with carbon-based molecules, including methane and carbon monoxide, at levels far exceeding those found on any planet in our solar system. This abundance of carbon is so extreme that scientists believe it could lead to the formation of diamonds deep within the planet's atmosphere. Imagine a world where the skies are filled with the building blocks of precious gems, a place where chemistry takes on a dazzling, almost surreal form. What makes WASP-12b's carbon-rich atmosphere so fascinating is its implications for planetary science. On Earth, carbon is a key ingredient for life, but on WASP-12b, it dominates the atmosphere in ways that challenge our understanding of planetary formation. The planet's close proximity to its star, so close that it completes an orbit in just over one Earth day, creates scorching temperatures that vaporize carbon compounds, allowing them to accumulate in the atmosphere. This intense heat also causes the planet to puff up, giving it a bloated, almost inflated appearance. But the story doesn't end there. WASP-12b is slowly being devoured by its star, a process that's stripping away its atmosphere and leaving behind a comet-like tail of gas. This ongoing destruction adds another layer of intrigue to the planet's already bizarre chemistry. As the atmosphere is pulled away, the carbon-rich material could condense into solid forms, potentially creating diamond-like structures in the process. It's a cosmic alchemy that turns destruction into something beautiful and scientifically groundbreaking. Studying WASP-12b offers a unique window into the diversity of planetary atmospheres. It challenges our assumptions about how planets form and evolve, especially in extreme environments. By understanding the chemistry of carbon-rich worlds like WASP-12b, we can gain insights into the potential for exotic materials and processes on other planets. It's a reminder that the universe is full of surprises, and even the most familiar elements can behave in extraordinary ways under the right conditions. As we marvel at the diamond-forming potential of WASP-12b, we're reminded once again of the boundless creativity of the cosmos. From storms that dwarf our hurricanes to atmospheres that could rain gems, the universe continues to push the boundaries of what we thought was possible. Next, we'll explore a planet with a year so long it outlives its own star, a celestial oddity that defies the very concept of time. Now, let's turn our attention to a planet that seems to exist in defiance of time itself, a world where a single year stretches longer than the lifespan of its own star. Meet PSRB 1600-2026b, a planet located in the globular cluster Messier 4, approximately 12,400 light-years from Earth. This ancient world orbits a binary star system, but here's the twist. One of its stars is a pulsar, a rapidly spinning neutron star, and the other is a white dwarf. Together, they form a celestial duo with a lifespan far shorter than the time it takes for PSRB 1600-2026b to complete just one orbit around them. PSRB 1600-2026b's orbital period is staggering. It takes roughly 100 Earth years for this planet to circle its binary stars. But the pulsar and white dwarf at the heart of this system have already lived out their main phases of stellar evolution. The pulsar, born from the explosive death of a massive star, and the white dwarf, the cooling remnant of a sun-like star, are now in the twilight of their existence. This creates a fascinating paradox. How can a planet with such a long orbital period exist in a system where its stars have already burned out? The answer lies in the planet's unusual history. PSRB 1600-2026b is believed to be one of the oldest known exoplanets, with an estimated age of around 13 billion years, nearly as old as the universe itself. It likely formed early in the history of its star system, long before the pulsar and white dwarf came into being. Over billions of years, the planet survived the violent transformations of its stars, including the supernova explosion that created the pulsar. This resilience makes PSRB 1600-2026b a cosmic survivor, a relic from a time when the universe was still in its infancy. The existence of PSRB 1600-2026b challenges our understanding of planetary formation and survival. Most planets form in the relatively stable environments of young star systems, but PSRB 1600-2026b has endured through cataclysmic events that would have destroyed less hardy worlds. Its survival raises intriguing questions about the durability of planets and the conditions necessary for them to persist over billions of years. Could there be other ancient planets like this one, hidden in the depths of the cosmos, waiting to be discovered? Studying PSRB 1600-2026b also provides a unique glimpse into the dynamics of binary star systems. The gravitational interactions between the pulsar, white dwarf, and planet are complex, offering insights into how such systems evolve over time. This planet's existence suggests that even in the most chaotic environments, planets can find a way to endure, adapting to the changing conditions around them. As we ponder the mysteries of PSRB 1600-2026b, we're reminded of the incredible resilience of celestial bodies. This ancient planet, with its year longer than its star's lifespans, stands as a testament to the enduring nature of the cosmos. Next, we'll explore a planet where fire and ice coexist in a bizarre and unexpected harmony, a world that defies our understanding of planetary surfaces. Now, let's venture into the realm of a planet where the laws of nature seem to collide in the most extraordinary way. Imagine a world where fire and ice exist side by side, not as opposites but as partners in a cosmic dance. This is Gliese 436b, a planet that defies our understanding of planetary surfaces with its bizarre and seemingly contradictory conditions. Gliese 436b, located approximately 33 light-years from Earth, is a Neptune-sized exoplanet orbiting a red dwarf star. What makes this planet truly remarkable is its surface, which is covered in what scientists call burning ice. At first glance, the idea of burning ice sounds like something out of science fiction, but the science behind it is both fascinating and real. The key to this phenomenon lies in the extreme conditions on Gliese 436b. The planet orbits incredibly close to its star, completing a full orbit in just 2.6 Earth days. This proximity subjects the planet to intense heat, with surface temperatures soaring to around 800 degrees Fahrenheit. Under normal circumstances, such temperatures would vaporize any ice, but Gliese 436b is far from normal. The immense gravitational force exerted by the planet creates an atmosphere of extreme pressure, estimated to be hundreds of times greater than Earth. This pressure forces water molecules into a solid state, even at temperatures that would typically turn them into gas. The result is a form of ice that remains solid despite the scorching heat, earning it the name hot ice or burning ice. But the strangeness doesn't end there. The intense heat from the star causes the ice to sublimate, turning directly from a solid into a gas. This creates a thin, steamy atmosphere that envelops the planet, adding another layer of complexity to its already peculiar environment. The interplay between heat, pressure, and water molecules on Gliese 436b challenges our understanding of the states of matter and how they behave under extreme conditions. Gliese 436b's unique characteristics also provide valuable insights into the diversity of exoplanets. It serves as a reminder that the universe is full of surprises, often defying the rules we've come to expect based on our own solar system. The discovery of burning ice on this planet has expanded our knowledge of planetary science, showing us that even the most familiar substances like water can behave in extraordinary ways under the right conditions. As we marvel at the mysteries of Gliese 436b, we're reminded of the boundless creativity of the cosmos. This planet, with its surface of burning ice, stands as a testament to the incredible variety of worlds that exist beyond our own. Next, we'll uncover the secrets of a planet with a magnetic field so powerful it rivals even the mightiest in our solar system, a world that continues to push the boundaries of what we thought possible. Now, let's turn our attention to a planet that doesn't just push the boundaries of what we know. It shatters them entirely. Meet HAT P7b, a world with a magnetic field so powerful it dwarfs even Jupiter's, the strongest in our solar system. This discovery isn't just a testament to the planet's unique nature. It's a window into how magnetic fields can shape the environments of distant worlds in ways we're only beginning to understand. HAT P7b, located about 1,040 light-years from Earth, is a gas giant that orbits its star in just 2.2 Earth days. Its close proximity to its star subjects it to extreme temperatures, with its dayside reaching scorching highs of over 4,000 degrees Fahrenheit. But what truly sets this planet apart is its magnetic field, which is estimated to be several times stronger than Jupiter's. Magnetic fields play a crucial role in shaping a planet's environment. On Earth, our magnetic field protects us from harmful solar radiation and helps maintain our atmosphere. On HAT P7b, the magnetic field is so intense that it creates dramatic and dynamic interactions with the planet's atmosphere and its host star. One of the most striking effects of this powerful magnetic field is the way it influences the planet's atmosphere. HAT P7b is tidally locked, meaning one side always faces its star while the other remains in perpetual darkness. The magnetic field channels heat from the scorching day side to the cooler night side, creating violent storms and atmospheric currents that rage across the planet. These storms are so intense that they can even alter the planet's brightness, making it appear to flicker when observed from afar. But the influence of HAT P7b's magnetic field doesn't stop at its atmosphere. The field also interacts with the charged particles streaming from its star, creating auroras that would put Earth's northern lights to shame. These auroras aren't just beautiful, they're a sign of the complex interplay between the planet's magnetic field and the space environment around it. The discovery of HAT P7b's magnetic field has profound implications for our understanding of exoplanets. It challenges the assumption that only massive, Jupiter-like planets can generate strong magnetic fields and opens up new questions about how such fields form and evolve. Could smaller planets also have powerful magnetic fields? And if so, what does that mean for their potential to support life? As we continue to study HAT P7b, we're reminded once again of the incredible diversity of planetary systems in the universe. This planet, with its magnetic might, stands as a testament to the dynamic and ever-changing nature of the cosmos. Next, we'll explore a world where the surface temperatures are so extreme they rival those of some stars, a planet that challenges everything we thought we knew about the limits of planetary heat. Now, let's venture into the realm of a planet so extreme that it defies the very definition of what a planet can be. Meet Celt 9b, a world where the surface temperatures soar to a staggering 4,000 degrees Celsius hotter than some stars. This isn't just a planet, it's a cosmic furnace pushing the boundaries of what we thought was possible for planetary environments. Celt 9b orbits a star located about 650 light-years from Earth, and its proximity to its host star is nothing short of extreme. The planet completes an orbit in just 1.5 Earth days, meaning it's so close to its star that it's practically being roasted alive. The day side of Celt 9b is bombarded with intense radiation, heating its surface to temperatures that rival those found in the outer layers of some stars. What makes Celt 9b truly remarkable is how it challenges our understanding of planetary limits. Most planets, even gas giants like Jupiter, have temperatures that pale in comparison to the scorching heat of stars. But Celt 9b blurs the line between planet and star, existing in a category all its own. Its extreme heat causes its atmosphere to expand dramatically, creating a puffy, bloated appearance that sets it apart from other gas giants. The intense heat also has a profound effect on the planet's atmosphere. Molecules that would normally be stable on cooler planets are torn apart by the extreme temperatures, creating a chaotic and volatile environment. Hydrogen atoms, for example, are stripped away from the planet's atmosphere and lost to space, leaving behind a trail of ionized gas. This process, known as atmospheric escape, is happening at an unprecedented rate on Celt 9b, giving scientists a rare glimpse into how planets can lose their atmospheres under extreme conditions. But the challenges posed by Celt 9b don't stop there. The planet's extreme heat also raises questions about its long-term survival. With its atmosphere being stripped away and its surface temperatures reaching levels that would vaporize most known materials, Celt 9b may not exist in its current form for much longer, at least on a cosmic timescale. This raises intriguing questions about the lifespan of such extreme planets and how they fit into the broader picture of planetary evolution. The discovery of Celt 9b has forced astronomers to rethink what they know about planetary systems. It challenges the assumption that planets must exist within a certain temperature range and opens up new possibilities for understanding the diversity of worlds in the universe. Could there be other planets out there, even hotter than Kelt 9b? And what does this mean for our search for habitable worlds? As we continue to study Kelt 9b, we're reminded once again of the incredible extremes that exist in the cosmos. This planet, with its blistering heat and volatile atmosphere, stands as a testament to the dynamic and ever-changing nature of the universe. Next, we'll explore a world that may hold the key to one of the most tantalizing questions in astronomy. Could there be life beyond Earth? Now, let's turn our attention to a discovery that brings us closer to answering one of the most profound questions in science. Could there be life beyond Earth? Meet Kepler 1625b, a planet that has captured the imagination of astronomers and space enthusiasts alike, not just for itself, but for what might be orbiting it, a moon that could potentially host life. Kepler 1625b is located approximately 8,000 light-years from Earth, and while the planet itself is a gas giant much larger than Jupiter, it's the possibility of a moon that has scientists buzzing. This potential moon, unofficially dubbed Kepler 1625bi, is estimated to be about the size of Neptune, making it one of the largest moons ever detected if confirmed. What makes this moon so intriguing is the possibility that it could have liquid water, a key ingredient for life as we know it. The idea of a moon hosting life isn't as far-fetched as it might seem. In our own solar system, moons like Europa and Enceladus have shown signs of subsurface oceans, making them prime candidates in the search for extraterrestrial life. Kepler 1625bi, if it exists, could be another such world. The moon's size and distance from its host planet suggest that it might have the right conditions to maintain liquid water, especially if it has a thick atmosphere or internal heat sources like tidal forces. The discovery of Kepler 1625bi was made possible through observations by the Hubble Space Telescope, which detected subtle dips in the light from the planet's host star. These dips hinted at the presence of a moon, but confirming its existence is no easy task. The data is still being analyzed, and while the evidence is promising, scientists remain cautious. If confirmed, this would be the first exomoon ever discovered, marking a monumental milestone in astronomy. The implications of such a discovery are staggering. If Kepler 1625bi does indeed have liquid water, it could open up entirely new avenues in the search for extraterrestrial life. It challenges our assumptions about where life might exist, suggesting that even moons orbiting gas giants could be habitable. This expands the potential number of places in the universe where life could thrive, making the cosmos feel just a little less lonely. But the search for life on Kepler 1625bi is just beginning. Future telescopes like the James Webb Space Telescope could provide more detailed observations, potentially revealing the moon's atmosphere and even signs of water or organic molecules. Each new discovery brings us closer to answering the age-old question, are we alone in the universe? As we ponder the possibilities of Kepler 1625bi, we're reminded of the incredible diversity of worlds that exist beyond our solar system. This potential moon, with its tantalizing hints of habitability, represents a new frontier in our quest to understand the cosmos. Next, we'll explore a planet that takes extreme conditions to a whole new level, a world where the surface is so hot it might be covered in molten iron. Now let's venture into a world where the very ground beneath your feet would be a sea of molten metal. Meet Co-Rho T7b, a planet that takes extreme to a whole new level. Located about 489 light-years from Earth, this rocky exoplanet orbits so close to its star that its surface temperatures soar to unimaginable heights, so hot, in fact, that it might be covered in molten iron. Co-Rho T7b is what scientists call a super-Earth, a term used for planets larger than Earth but smaller than gas giants like Neptune. But don't let the name fool you, this planet is anything but Earth-like. Its surface is a scorching inferno with temperatures reaching up to 2,500 degrees Celsius on its day side. That's hot enough to melt rock and metal, creating a landscape that's more like a bubbling cauldron than a solid surface. What makes CoRoT T7b so extreme is its incredibly tight orbit. It completes a full trip around its star in just 20 hours, meaning a year on this planet is shorter than a single day on Earth. This proximity subjects the planet to intense gravitational forces, which likely keep one side perpetually facing the star, while the other side remains in eternal darkness. The day side is a molten hellscape, while the night side might be cold enough to solidify some of the molten material, creating a stark contrast between the two hemispheres. The extreme heat on CoRoT T7b doesn't just melt its surface, it also vaporizes rock, creating a thin atmosphere of silicate vapor. Imagine a world where the air itself is made of the same material as sand or glass. This bizarre atmosphere, combined with the planet's molten surface, makes CoRoT T7b one of the most hostile environments ever discovered. But how does a planet like this even form? Scientists believe CoRoT T7b might have started as a gas giant, similar to Jupiter or Saturn, before migrating closer to its star. Over time, the intense heat and radiation stripped away its gaseous layers, leaving behind a dense, rocky core. This process, known as photoevaporation, could explain why CoRoT T7b is so close to its star and why its surface is so extreme. The discovery of CoRoT T7b challenges our understanding of planetary formation and evolution. It shows us that planets can exist in conditions we once thought impossible, pushing the boundaries of what we consider habitable or even survivable. While CoRoT T7b is far from a candidate for life, its existence reminds us of the incredible diversity of worlds in the universe, worlds that defy our expectations and expand our imagination. As we leave the molten surface of CoRoT T7b behind, we'll journey to a planet where time itself seems to stretch to infinity. Next, we'll explore HD 106906b, a world with an orbit so vast that a single year lasts 11,000 Earth years. Now, let's shift our gaze to a planet where time moves at a pace almost beyond comprehension. Meet HD 106906b, a world so distant from its star that a single year lasts an astonishing 11,000 Earth years. Located about 336 light-years away in the constellation Crux, this planet defies everything we know about typical planetary orbits. HD 106906b is what astronomers call a super-Jupiter, a gas giant with a mass roughly 11 times that of Jupiter. But what truly sets this planet apart is its orbit. While most planets in our solar system orbit their stars in relatively flat, circular paths, HD 106906b follows an elongated, tilted orbit that takes it incredibly far from its host star. At its farthest point, the planet is over 700 times the distance between Earth and the Sun. To put that into perspective, if you were standing on HD 106906b, its star would appear as little more than a bright dot in the sky. So, how does a planet like this even form? Traditional models of planetary formation suggest that planets coalesce from a disk of gas and dust surrounding a young star. However, HD 106906b's extreme orbit challenges this idea. One theory is that the planet formed much closer to its star but was flung outward by gravitational interactions with another massive object, such as a passing star or a companion planet. Another possibility is that HD 106906b formed independently, almost like a star, from a collapsing cloud of gas and dust, but didn't gather enough mass to ignite nuclear fusion. What's even more fascinating is how HD 106906b has managed to survive in such an unusual orbit. Gravitational forces from nearby stars or other celestial bodies could have disrupted its path, yet it remains stable. This suggests that the planet's system might be more complex than we initially thought, with unseen forces at play keeping it in place. The discovery of HD 106906b opens up new questions about the diversity of planetary systems. It shows us that planets can exist in orbits we once thought impossible, challenging our understanding of how planetary systems form and evolve. While HD 106906b is far from a candidate for life, its existence reminds us that the universe is full of surprises waiting to be uncovered. As we continue to explore the mysteries of HD 106906b, we'll delve deeper into the unusual dynamics of its orbit and what it reveals about the formation of distant planetary systems. Stay tuned as we uncover more about this enigmatic world and the secrets it holds. Now, let's take a closer look at the peculiar orbit of HD 106906b and why it's such a puzzle for astronomers. This planet's path around its star is unlike anything we've seen before. While most planets follow relatively flat, circular orbits, HD 106906b takes a wildly different route. Its orbit is not only highly elongated but also tilted at an extreme angle compared to the plane of its star's system. This means the planet swings far out into the depths of space, only to loop back in a way that defies our expectations of how planets should behave. What makes this orbit so baffling is that it challenges the very foundations of how we think planets form. According to traditional models, planets are born from a swirling disk of gas and dust surrounding a young star. Over time, this material clumps together, eventually forming planets that settle into stable, circular orbits. But HD 106906b's orbit is anything but stable or circular. Its extreme distance and tilted path suggest that something extraordinary must have happened during its formation. One leading theory is that HD 106906b was once much closer to its star but was flung outward by a dramatic gravitational encounter. Imagine a cosmic game of billiards where a passing star or a massive companion planet gave HD 106906b a gravitational kick, sending it hurtling into its current orbit. This kind of event would explain why the planet is so far from its star and why its orbit is so irregular. Another possibility is that HD 106906b didn't form in the traditional way at all. Instead, it might have come together independently, almost like a star from a collapsing cloud of gas and dust. However, it didn't gather enough mass to ignite nuclear fusion, leaving it as a massive planet rather than a star. This scenario would also explain its unusual orbit, as it wouldn't have formed within the typical disk of material surrounding its star. What's truly remarkable is how HD 106906b has managed to maintain its orbit over billions of years. Gravitational forces from nearby stars or other celestial bodies could have disrupted its path, yet it remains stable. This suggests that the planet's system might be more complex than we initially thought, with unseen forces or structures helping to keep it in place. The discovery of HD 106906b forces us to rethink our understanding of planetary systems. It shows us that planets can exist in orbits we once thought impossible, challenging our assumptions about how these systems form and evolve. While HD 106906b may not be a candidate for life, its existence reminds us that the universe is full of surprises waiting to be uncovered. As we continue to explore the mysteries of HD 106906b, we'll delve deeper into the role of gravitational interactions and how they shape the orbits of distant planets. Stay tuned as we uncover more about this enigmatic world and the secrets it holds. Now, let's turn our attention to the forces that might have sculpted HD 106906b's bizarre orbit. Gravitational interactions with other celestial bodies could hold the key to understanding how this planet ended up so far from its star and on such an unusual path. In the vast dance of space, gravity is the choreographer, and sometimes its moves can be unpredictable. One possibility is that HD 106906b's orbit was shaped by a close encounter with another massive object, such as a passing star or a large planet. Imagine two dancers colliding mid-performance, sending one spinning off in an unexpected direction. In the case of HD 106906b, a gravitational nudge from a nearby star or a massive companion planet could have flung it into its current elongated and tilted orbit. This kind of interaction would explain why the planet is so far from its star and why its path is so irregular. Another intriguing idea is that HD 106906b's orbit was influenced by the gravitational pull of multiple objects over time. In a crowded stellar neighborhood, the combined forces of nearby stars, planets, or even remnants of the planet-forming disk could have gradually pushed the planet into its current position. This process, known as gravitational scattering, is like a cosmic tug of war, where the planet is pulled in different directions until it settles into a stable, albeit unusual, orbit. What's fascinating is that HD 106906b's orbit has remained stable despite these potential disruptions. This suggests that the planet's system might have a hidden structure or mechanism that helps maintain its balance. For example, there could be an unseen companion, such as a distant star or a massive planet, whose gravity counteracts the forces that might otherwise destabilize HD 106906b's orbit. Alternatively, the planet's extreme distance from its star might shield it from significant gravitational disturbances, allowing it to maintain its peculiar path over billions of years. The study of HD 106906b's orbit also sheds light on the broader dynamics of planetary systems. It shows us that planets don't always follow the neat, circular paths we expect. Instead, their orbits can be shaped by chaotic and unpredictable events, such as close encounters or gravitational interactions with other objects. This challenges our traditional models of planetary formation and evolution, forcing us to consider a wider range of possibilities. As we continue to explore the mysteries of HD 106906b, we'll gain deeper insights into the role of gravity in shaping planetary systems. This enigmatic world reminds us that the universe is full of surprises, and that even the most unusual orbits can teach us something new about the cosmos. Next, we'll delve into the implications of HD 106906b's discovery for our understanding of exoplanets and their formation. Stay tuned as we uncover more about this fascinating planet and the secrets it holds. Now, as we reflect on the significance of HD 106906b, it's clear that this distant world has reshaped our understanding of planetary systems. Its peculiar orbit challenges the traditional models we've relied on for decades, forcing scientists to rethink how planets form and evolve. This discovery isn't just about one planet. It's a window into the chaotic and dynamic processes that shape the cosmos. HD 106906b's existence suggests that planetary systems are far more diverse and unpredictable than we once imagined. Its extreme distance from its star and its tilted, elongated orbit defy the neat, orderly patterns we often associate with planetary formation. This raises important questions about how such systems come to be. Could there be more planets like HD 106906b lurking in the outer reaches of other star systems? And if so, what does that mean for our understanding of the universe? One of the most exciting implications of this discovery is the role of gravitational interactions in shaping planetary systems. HD 106906b's orbit hints at the influence of unseen forces, such as passing stars or massive companion planets, that can dramatically alter a planet's path. This opens up new avenues for research, encouraging scientists to explore how these interactions might explain other unusual planetary systems. Moreover, HD 106906b reminds us that the universe is full of surprises. Its discovery underscores the importance of continuing to search for and study exoplanets, especially those that don't fit the mold. Each new finding adds another piece to the puzzle, helping us build a more complete picture of how planets form, evolve, and interact within their systems. As we look to the future, HD 106906b serves as a powerful reminder of how much we still have to learn. It challenges us to push the boundaries of our knowledge and to remain open to the unexpected. After all, the universe is vast and its mysteries are endless. Who knows what other strange and wondrous discoveries await us as we continue to explore the cosmos? With that, we've reached the end of our journey through 25 of the strangest discoveries about planetary systems. From diamond planets to worlds with triple suns, each of these findings has expanded our understanding of the universe in its own unique way. If you've enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more space mysteries. Until next time, keep looking up, there's always more to discover. As we wrap up this journey through 25 of the strangest discoveries about planetary systems, it's impossible not to marvel at how much these findings have reshaped our understanding of the cosmos. From the diamond-studded surface of 55 Cancri E to the mind-bending orbit of HD 106906b, each discovery has pushed the boundaries of what we thought was possible. These worlds remind us that the universe is far more diverse, chaotic, and unpredictable than we ever imagined. These discoveries don't just challenge our existing theories, they force us to rethink the very foundations of planetary science. How do planets form in such extreme environments? What processes create worlds with molten iron surfaces or atmospheres that rain glass? And what other bizarre phenomena are waiting to be uncovered in the vast expanse of space? The beauty of these findings lies in their ability to spark curiosity and inspire further exploration. Each strange world we uncover is a piece of a much larger puzzle, helping us build a more complete picture of how planetary systems evolve. But with every answer comes a new question, and that's what makes the study of space so endlessly fascinating. So, as we close this chapter, let's leave you with one final thought. What other mysteries are hiding in the depths of the universe? Could there be planets with even more extreme conditions, or perhaps worlds that defy our understanding entirely? The possibilities are as limitless as the cosmos itself. If you've enjoyed this journey through the strange and wondrous worlds beyond our solar system, don't forget to share your thoughts in the comments below. What discovery fascinated you the most? And if you're eager for more space mysteries, be sure to hit that like button, subscribe, and ring the notification bell so you never miss an update. Until next time, keep your eyes on the stars. There's always more to discover.